So you can see the picture. So if the person's CA, C means the number of years since birth. The CA is 35, but his biological age, the BA is 40, means his BA greater than his CA. So he has a shorter healthy span. And if the person CA is 35 and his BA is 30, means his biological age is less than CA, so it means he has longer health span. So an aging clock is a scientific tool that estimates the biological age, and the biological is often gives a more accurate picture of a person's health than CA. Aging clocks use various biomarkers such as blood tests, gene data, and metabolic indicators to predict a person's aging process and potential health risks. So why use aging clock to measure biological age? First is the limitation of traditional methods. Traditional healthy methods often focus on specific disease or individual biomarker like genes or blood pressure. However, these methods fail to capture the complexity of the entire body. That's where aging clocks become useful. They can give a more comprehensive view of a person's overall aging process by analyzing multiple health factors. The importance of aging block, I think I don't need to repeat it.
You can be slightly louder.
Oh, okay. So this paper, first let me introduce the current method. First is a chrono age. That means CA that I introduced before. It's refers to the actual number of years a person has allowed since birth. That means I born in 1996, so my CA is 28. And there is also a final age. One example of aging clock. The definition is that final age is an estimate of a person's biological age based on biomarkers and clinical data. Final age is calculated using 9 clinical markers such as white blood cell count and so on. Its purpose is to predict an individual's future health risk and lifespan more accurately than chrono age. And this paper has introduced the PC age. So what is PC age? PC age, on the other hand, is built using PCA. The PCA is very famous and traditional machine learning methods. It's not the key point in this presentation. So I just introduced it here, which is a dimensionally reduction technique. It looks at a much larger data set, 165 clinical parameters from health examination, blood chemistry, and physical measurements. And the PCH extracts 18 pre-simple components that explain 99% of the variance in the dataset, meaning it compresses the data while remaining the most relevant information about aging. And the pre-simple components, along with the individual's CA, were used in Cox model to predict each person's risk of death. This is the definition of the PCH, and we can go on. I think the most important part in this paper is how they use the PCH to do a series of analysis. And let me introduce it. First, let me introduce the dataset in this paper. The training dataset is using the NHANES4.
For people working on the medical side, in this data set, in the survey data from US,
Yes.
and it's mostly publicly available, and it's actually a very valuable data set, even though it's publicly available.
Yes.
For many studies for Yeah, I mean, you can see they can publish a Nature agent paper, simply use a public available data.
Yes. Yes, this set, I'm not sure how many he includes the parameters, but this paper uses the 186 clinical parameters. And he also uses a self health index and a healthcare use index. So the next is the results of this paper. And it's all figures, and I think the figures is very beautiful. Yeah, and first you can see the left picture. As expected, PCH was highly correlated with CA in both males and females, but with very large residues. You can see the picture in the left. It means the X is the CA and the YX is the PCH. It has very high correlation. And the picture in the left right is
Sorry.
yes.
Chronic age is the actual age, right? And
Yes.
what is PCH? I forgot the definition.
PCH is this paper
The
represents
phenotypical age,
Phenotype.
phenotype age, which is I think that's the
Biological.
no, the PCH is this is the definition.
PCH exactly is in physical
Yes,
components.
this is
so they have some variable from patients, different age, gender, smoking, BMI kind of thing. Then there's a PCA on it.
Yes,
PCH is principal component of the
yes.
18 principal components explain the when they are plotting x-axis and y-axis is single scalar value, right?
So which they have 18 principal degree or 18 or only the one of them.
Yeah, they use 18 and they use 18 parameters to train the Cox model, and the weights used in the.
Okay, so about age, chronological age is not in this principal component, right?
He uses it.
Oh, really?
Yes. Chronological age. Yes, I think he uses it.
Whatever.
Along with the yes, they also used in the Cox model. This here, you can see that.
Oh, I see.
Also.
So basically, they use those 18 principal components plus chronological age.
So this is different from PCH, right? From age.
Yeah, chronological age. It says the year.
Chronological age, the real age.
Yeah, your age.
Number of years. Yeah, the one on your ID.
Yes. Okay. Okay. And the right picture, he do analysis is to show that the CA chronological age CA and the PCH, which present in this paper, were both significantly negative correlated with telomere length, chronologic performance, and gain speed. That means your CA and the PCH is going bigger, and then your chronological performance will decline. It's very makes sense. I think it's very easy to understand. That means your grade you'll be older and your cognitive performance will decline. And this next he also do a analysis about the performance of the PCH in predicting survival is in unknown subjects by selecting subjects in the test cohort within the best 25% and worst 25% quotas for BA. This is very common analysis method in the medical papers.
So why?
Yes.
This is for everyone, all individuals in the cohort?
Yes, it is everyone's average of everyone's survival probability.
So your PCH, then what is the uniqueness of PCH here?
You
So what's the value of the PCH?
the survival probability.
But that's a high PCH, right?
Yeah.
You have a high PCH.
Yes.
Then you have a less likely, you're more likely to die. You have a low risk.
Yes.
You're more likely to die. But that doesn't do much better than the other thing, right? Even your chronological age show reasonable performance, but your cardiovascular disease, high, low, also give a good result. There's only one type of disease. If you put cardiovascular or cancer, other thing together, probably more worse.
PCH performs better than CVD risk.
But CVD is only one type of disease.
Yes.
If you do CVD plus cancer, you break it down everything.
Yes, this is just one. I think one example of this analysis. And this.
You should something from this. I think you probably heading to the same direction. Apart from your biomarker used in the study.
The PCH high and PCH low means I can isolate here with the best 25% and the worst 25% quarter of the biomarker. So the PCH high, so you can see that it has the low survival probability. It makes sense because PCH high means your health is not very good, so your survival probability is lower than other.
So exactly the same line for your study.
Yes.
But to change the y-axis to that's still, but we need to change the y-axis to, like, for example, in my case, it's also
Yes, but in Ting Xu's settings, literally just survival.
okay.
Yeah.
Yes.
And you can include the black line chronological age.
So basically, how can we tell from this graph, like, how good is the method? Is that the ability that is able to split the low risk part and the high risk part?
I think that's their logic. I don't buy it, but I think that's their logic.
Okay.
This is common in public health setting. The line show separate better to the high risk and low risk one better.
Okay.
Yes.
I mean, it's a bit like if you think about machine learning wise or statistical wise, the contribution is limited, right? Because your blue color line already contain information about the black color line, and all information about cardiovascular disease as well. So it should perform better than this. So you have more variable.
Oh yeah.
Of course. I mean, for people on the public health side, they don't know how to do this. I mean, this might be something very useful for them. Okay.
So this graph basically looks like separates two classes.
Yep.
The more is able to separate two classes, the better.
Sometimes they do 4 classes.
Oh, okay.
Quarter 1, 2, 3, and 4, and see how well we separate them.
Oh, I see.
Yes.
So here it says that the plot is proportional to the PCH, right? So is it, I mean, you are saying that PCH is better than the chronological age, but PCH is also positively correlated with the chronological age, right?
That's right.
So then chronological age is itself enough, right? Why we have to go for PCH?
So they put more variables into
Yes.
this blue color line. So it can separate high risk and low risk patients better.
I have a question. PCA is suitable for linear decomposition.
Yeah. So
Yeah.
there are many assumptions in PCA. I think Euclidean distance is also one of the assumptions in PCA. Yeah.
I think the reason is that the age is the standard criteria for the predict the health and death. So this PCH improves the age, I think accuracy of another thing, improves the age age.
So somehow this public health people, they like to separate high risk and low risk people, and as long as you allow them to achieve the goal, the simplest the better. This is different from the machine learning field, right? To put to build parameter, and here is like as long as you can get the work done, simpler the better. There's slightly different strength. Remember, this is nature agent. Yeah, it's probably give you a very good information somewhere.
So the real number of the probability here in this graph actually does not make any sense. The really matters is the relative probability.
You have to put some baseline here to beat those baseline. You can see the previous the cardiovascular disease baseline, the beat the chronological age. I mean, that only have one line, but yeah, I mean, you can see the baseline is really just the cardiovascular disease.
Okay, I think. I mean, for example, the survival probability number, for example, 50%, it does not necessarily mean the person have a 50% chance of dying.
That population, that blue color population has 50% chance of survival cumulatively. Okay, yeah.
That means the 200 follow-up months, all of the people and 1,500 will survive is percent, 50%. Yes.
And one more thing,
Yeah.
these thick lines are these are the probability values, these thick lines.
Thick line.
What is the dark lines?
Dark.
Dark curves.
Dark, you mean the CAH?
For example, everywhere there is, for example, if you look at a blue curve,
Yes.
there is a dark curve and there is a variance thing, right? Lighter color. You understand? If you look at any graph, let's say E color,
E color.
E plot, okay?
block.
And there is a blue
Yeah.
color, right?
Yes,
And there is also light blue color.
yes.
So this blue color is the probability which you computed from the Cox model, I guess.
Box model.
POX.
You see the
The
line.
line.
Oh, it's
values.
the KM. It also has a model, the KM survival. Survival covers.
Okay.
It has a
What is
clinical
the lighter color represents?
light color.
Blue is the mean.
I think it's
Like how the variance is computed. Why? Because it's already the probability, right?
Yeah, it's like the blue color line. Each of the line
As some variance.
contain more than one human. It's population of people.
Mm.
So that's where the survival, those variance, confidence interval comes from.
virus. Yes,
It's actually mainly line, but you smooth it. Then you have
Mm.
confidence interval. Okay.
yes.
Yeah, this is the public health field. It's like the logic is slightly different from the cheaper you can probably see the data processing is much simpler than biology. Yeah, but if you understand the data artificial processing can finish in a week in terms of data processing. Typical part is picking the problem. Yeah.
Okay, let me continue. Okay, we can see this picture. I think this picture is very good. Seems very good. And so for each CA being PCH for male and female population proceeds along here towards the right and contain distinct subpopulations of subjects who were significantly biological older. Okay, let me just explain the picture. The XXL is the male. The first picture is about all the people is the male. The XXL is the PCH and the YXL is the age, the CA age is the CAD. So, for example, the first line in the bottle is means his CA is between 40 and 60, and you can see the line in the PC age is between the 20 and more than 60.
That means some people even they have some same real age,
Yes.
but their biological age are much older than other people.
Yes.
And there's always this small group of people who are older
Yes. Yes.
compared to the majority of people.
Yes.
Who are they? Who are those people?
They have this analysis. You can see this. the figure particularly focus on the individuals whose PC age is 20 years or more greater than their actual age. And the group is more easy to age-related disease. He has some analysis the median comorbidity index of 0.18 and significantly higher than the age and sex matched control group. Yes, I think it has makes sense.
So, what are the characteristics of those people?
They have the people's the information.
Yeah, but what are the information? This tells us, I mean, they are more susceptible to diseases. So
Yes.
what are the unique features of those people?
It-
Are they fatter, or do they smoke, or do they drink alcohol, or?
In this paper, they haven't analyzed as this part.
That's the most interesting part.
Yeah, that is what we need to know.
Yeah, that's a public opinion. That's a public health paper.
Actually, in the next part, they have analyzed this. Yes. And I think this analysis it makes sense. For example, it's pretty the PC age larger than the CA, so they have more easy to have age-related disease. And they also have a significant increased risk of death. Yes, this is this analysis. What's next?
So sorry, in the previous slide, okay, they predicted that PCH is whatever is predicted. I mean, in the 20 years, they're more probable of getting disease, right? So is there any way to verify their claim?
Oh, this guy they have the record of
Okay,
what
okay.
happened to this guy later.
Yes.
And this is 2020,
2022, I guess.
2002, right?
Yeah.
But they have until last year.
Okay.
This is already happen every single year.
Yes.
That's why this data set is very valuable. It's
Mm.
longitudinal. So one of the most precious things in medicine is longitudinal public health data. Don't have many of those.
Okay, this picture, phenol age is a traditional biomarker. So the first picture, figure B, is shows that PC age is high correlated with phenol age. That is what it wants to say. And the picture C means the compared the relative error sensitive or PC age, phenol age, and the ASCVD score. This score is also traditional score to evaluate a person has the CVD related disease, the score.
So I think figure D here is what for you and the Ting Xu trying to aim your study.
Yes.
So I don't know what baseline you need for me, but Ting we are probably clear about the baseline should beat.
Yes.
Yeah.
Yes, this D and
So, like how to beat the baseline, like they're making some
So you
prediction.
can see the figure D, right?
Like
D. The middle two line, they are baseline. And the orange and the green one, they are this PCH setting.
Okay.
The more separate they are, the more useful it is. Because the whole point of public health is to separate high risk people asking to see doctor, low risk people stay at home. Yeah, that's what I do. So separate high risk people well and better than the baseline in the literature, which is the phenol age. Now we have this death age. I think hopefully she can beat all of them. Then we go nature aging. Even though I know nothing about aging, but we'll do that.
Okay, this picture. Sorry. This I think it doesn't easy to see what the picture see, and they have the 1, 2, 3, 4, 5 clusters, and each cluster means I have a right in the right of the slide. The healthy.
How do they do the clustering?
Oh yes, they just class it for example, health aging might they have the information for every person, each person.
But the hundred, there are 5 or 4 clusters. It's hyperparameter.
Oh.
Yeah, so if you do k-means clustering, you have to know there's a k number.
Yes.
If you do similarity fusion, you have to know affinity.
Oh, they just definition I split in 5 clusters and
Why not 6, why not 4?
I'm not sure he just
Oh, okay.
specifically if
That's-
analyzed in the
that's
paper.
That's important. So when you're writing this paper, now you're writing your own paper like this. You have to know because someone may ask same question. For example, I was some reviewer of some major paper. If I ask this question in the concurrence, I would say no. Yeah. So
In K-means actually there's a method called elbow, I guess. I forgot.
yeah,
I mean the
the
plot.
kink, right?
Yeah,
The kink.
I forgot. If there's a, I mean you try for every K and you find the optimal K for it. There is a you have to
There's
plot
some value like you maximize the distance between cluster, minimize distance within cluster, put a balance on it. When you reach the best balance, you stop. That's a K value. Yeah.
I have a question. So the cover is a class of, I mean, the cover class is, so it's predefined by so it's just from the data set.
Yes.
Okay, so they do the cluster first and they add the color and they see that it's separated. It's
Yeah.
their logic.
Yes, I think yes. Right. And I think this picture is not very easy to see. You can see this is also have 5 clusters. It's the same with the previous slide. And you can find the cluster 1. Cluster 1 means let's see that. You can see the class 4, but class 4 health aging cluster is which is the green color. It shows that it has the higher survival probability. It makes sense because it's a health age cluster. And the red is the cardiometabolic fear cluster. Yes, the people with this disease often has the low survival probability. So the picture, I think the result is easy to understand. And the figure B is shows the relationship between CA and PCH for each male cluster. The slope represents the cluster specific aging rate. The health aging cluster which is the green one, has the slowest aging rate with an average increase of 1.03 years in biological age per year. And these 2 figures has shown the same thing. Yes, I think it's also seen the health age cluster has the high survival probability. And yes, this is let me see key pieces. You can see that this is the 5 clusters is PC means the PCA pre-simple components and his value. Yes, cluster. And from this table, we can find that the key pieces, particularly PC4 and PC2, were found to be important in discrediting the health aging cluster from other groups. And then the PC2 primarily captured difference related to body composition and fat, suggesting interventions like diet and exercise could promote the health aging. Yes, we need to diet and exercise. And the PC4, which correlated strongly with age and was higher in the less healthy clusters, included the markers related to cardiac function, kidney function, and inflammation and glucose regulation.
So the whole point of, for general public reading this paper is you should do exercise and
Yes,
diet.
yes, and diet. Actually, they have
Sleep.
no sleep.
No sleep.
Oh, actually, they have experiments said one group diet in 2 years and one group just eat free, and the group one has significantly show that they have the CVD. How to say it? The CVD disease, the 风险
Risk.
risk is low.
Oh, so, okay,
Decline.
actually, I think, one of the major, how to say, unique contribution from this paper, number one is the long tail from the distribution. Number two is that patient cohort matching analysis. But it's from the same data, but the match age, gender, and so on. So then you have low consumption of energy or carbohydrate, or calories. I don't know how to calculate, but then you have a healthier aging, healthier aging. I think that can we do that kind of thing in our study? It's very simple. Have two group of people, just matching age and gender. You are already doing that, right? Doesn't match a few more things and then analyze it. I don't know.
I think once we are good at, for example, separating the high risk of osteoporosis people from the non-osteoporosis people, we can analyze like what is the main difference between these two.
No, you want to match based on the intervention.
Based on intervention.
Yeah, in this case, in this paper is consumption of less carbohydrate or calorie. I don't know if you can tell us. In our case, I don't know, probably eat more egg or milk. In your case, for Ting's case, I don't know. Yeah, no one can tell the future about that.
But is there enough data for us to analyze this?
I mean, you can try, right? If you get that,
Yeah.
it's different between a cross medicine and a nature agent, right? So I think that I mean, everyone has that curves. Everyone has a curve, survival curve.
Yeah.
Right, but this long tail thing very rare to find, and this control study about intervention that's very rare to find. That's actually similar concept as preservation, cell preservation in the case.
Ting's program is about aging.
Yeah.
About aging. Actually, our lab in Beijing, Jiang's lab, we are doing something about using a human or classification, male or female blood PBMC sample.
Yeah.
To get single cell multi-omic data and estimate the biological age.
Yes.
Get data from them and ask them to take a picture of the IO candidate.
I can give you the data. I can give you the data.
Your next paper.
Yeah, single cell multi-omic data. Single cell RNA and single cell TCR. TCR is an antibody on the immune cell.
Oh, that's very important.
TCL. Yeah. TCR. Yeah.
Few body RNA or how many cell types?
How many cell types? It depends your classification.
Okay.
It can 10 or 100.
Okay, I see. Yeah. So I think that's very interesting project. How many individual people you have?
Too many. Nearly more than 100. More than 100.
Not very. Yeah,
sure. Is a range of age. Maybe 20 to 18.
Anyone have done the age analysis on it?
Sorry.
You have a data, right?
Yeah.
People are produced for some reason.
Yeah.
Has anyone already done agent analysis on it?
I'm not sure. I'm not aware.
But what's the purpose of the data produced?
Actually, I am not involved in that program.
Yeah.
So
what this data costs money, right? So why do you produce the data?
produce this data.
For what purpose?
For answer, biomarker in single cell level. In
For
biomarker.
biomarker for
Single cell level.
aging or for
Aging
aging.
biomarker. Yeah. Specific cell type and a specific biomarker.
Okay.
using single cell model.
We can discuss about, see if we can utilize something like that. Yeah, because this is private data.
Yeah.
Whenever you use private data, your contribution will become.
Yeah, so it is public. It is
It's
now public.
another project because recently we use the retinal fundus image to
Yeah, if
predict.
things can be connected somehow,
Yes,
right? That will make a very strong contribution.
yes, next
And I
step.
think about ways to connect if it's possible. Yeah.
Maybe we can discuss some details after.
Yeah. So let's literally say we should control how much we eat and run more.
Yes, exercise.
Okay, I believe we should sleep better. Don't get it. Don't get it.
Does this have the sleep data in it?
We haven't mentioned it. It's
I
sleep.
think they do.
Oh.
Okay, so there are few data sets you should be very familiar with if you work on AI medicine, right?
Mm.
UK Biobank, Mimic, and another one if you work on public health. This is one of them, right? This is literally the routine data set you should use. If you're so familiar with data, that's slightly different from machine learning side. Machine learning side, how familiar with your equations. This is different.
And the figure C and the scatter plot and line regressions of CA and visuals PC4 for each male cluster. The analysis is the same because the last slide is
So
shows
sorry, can you back to the slide?
this one
No, next one. Your figure D,
or figure D.
if you look at figure D, if we can get for this kind of analysis, there is a chance you can link this to the single cell results mentioned by Qifei. Right? You may not have every single data cell type here, but as long as you have a small portion of it, right? If your result agree with the single cell result, that's a huge thing. Yeah.
Yes, the figure
It
D.
is completely different analysis. Yeah. Think about it.
Figure D the signal is very clinical. Should I
Continue, please, continue.
continue? Okay. And let me see. This figure is also experiment. I think is also it's first have the experiment and then have the data, so we can use the PCH to do the analysis, not the analysis to not the also do the experiment for the analysis. And this is the two picture. You can, it's very clinical, hard to see. So I just see it in the easy way. This the red one is the healthy, and the the blue one is the healthy, and the red one is the person with the disease, but they haven't accepted the accepted the treatment. Sorry, sorry. And the green one is the people have the same disease, but they have accepted the treatment.
Sorry, so can you move into it?
Yes. As it has the disease is very hard to see the ECR.
Yeah, so in this data set, they have some treatment information inside.
Yes.
I think now, okay, so there are 3 people in our team working on content transformer project, right? That can be applied here.
Yes.
Yeah, of course, the data is not as detailed as in the new ICU analysis. This guy, this is not as good as the content transformer work we did because it simply matched the patients, but it still gave you some very good result in sense of novelty compared to the public health people.
I'm not sure about the data set. It's
Yeah, I'm
including
familiar with it. This is the data. It's this information whether it took this inhibitor, this drug or not. It's in the data set. And so Tim, this treatment effect part is the difference between nature aging and nature communication. Yeah, if we don't be like so, let's say paper driven, it's like the contribution between descriptive work this is useful suggestion or causal work to the community. Yeah.
Yes. Yes, this is a license. Any comments for this? Any question? It still have analysis so many figures. Let me see this pic.
Well, it's almost problem now, I think. Maybe you will wrap up in 2-3 minutes.
Okay, I think this is the same. This is also for sensitive analysis. That also created a simple biomarker, and he has done the same analysis as the previous slide. This one is the experiment I mentioned before for the Caroline restrict, and you can see that the Caroline Lynch law means the people who control their calorie in restrict, and you can see that they have a high survival probability. That means we do need to diet. And this is a experiment.
Thing is pointing to me.
Join us for half marathon. You still have a chance to.
Oh, yes.
Suggest it.
That's all. That's the
It's beginning of December. Yeah, you don't have to run all the way, right? Just finish it. Yeah, walk half of it. Still 20 kilometers.
oh yes, I think that's all. That's the main analysis of this paper.
This paper I actually shared to me with from one of my collaborators. I think this serves as a very good template, just in time for 2 projects we are working on.
Yes.
Between those of you, and I'll tell you how good. What's the maximum level you can achieve in this type of clinical research. I think you are doing better than they do. You are using a foundation model, a large transformer, plus fancy eye images to get a biomarker, and you have UK biobank data. They only have this survey data, right? You have treatment, UK biobank. Just maybe not that many people. If you want, you can dig it out. To be honest, I know this is painful. I did this myself before, but you have to get it to do this project, not even for medical biology project. You have to be very familiar with the data set. Yeah. So, and you have to spend time on, unfortunately, especially now, I'm collaborators say you should submit to nature biotech. You have no choice but number 1, dig into the biobank. Now, number 2, talk to one how you have to dig with that university now because nature biotech is not that easy. And this analysis, how many of them? I think we can borrow a lot of ideas from this paper, right?
Yes,
Analysis, and you have 2 baseline already. So one thing you have is easy for you, the 2 baseline are all from our group, I mean our department. Yeah, you can simply put on the same graph. If we can find something like this long tail,
yes, I think
that's treatment effects study. Yeah, with high chance. Yeah, and Gilbert Kramer is giving a talk in November in our department. I invited him. Can get him his name on the paper, then we don't have to connect with the London people. Can still get the good name, big name on our paper. Then. Yeah, plus population we should have enough spread into nature. Yeah. It's all up to you now.
working hard.
Yeah, it's not,
working.
not that important, but it's like make solid contribution to the field. Well, those are the things that Ting and Hongyu recently are working on. But we are how the major difference is actually how we get a biomarker. We use a much fancy way. We use it's like billion parameter foundation model. How big is foundation model now?
Oh, it's quite large. I think it's if you check the size of the checkpoint, it's about 3 gigabytes.
What's model is that pre-trained or
It's pre-trained.
It is
llama or
It's not.
No.
It's image only.
it's image?
Yeah, it's image only. I think
it's vision transformer based.
Oh wait.
So is that
from which company or so you're not using the
This is,
I
no,
think
I think this is the home trend.
do you use something like Qianwen or Llama
No,
LM
no.
something like that?
For this project, I think it's either from Momo or,
Yes.
so we home trained,
Home train.
yeah,
I see.
by, mask encoder
Uh-huh.
over transformer-based model
Ah,
on
I
all the eye images, because there are not that many of them,
Uh-huh.
probably something like 10 million images.
Uh-huh.
Home train that, then we, tune it in, for a specific task. Then we extract biomarker from it. And the team got 13 biomarker, we got like 1 or 2 biomarker. And we're trying to do, then that's the end of the the information extraction part. Then the rest of it is like that. Right? And the difference is they use PCA, we use something more advanced. And so this is what downstream about what they have already done. And yeah, how to make it full use of it. Yeah, and how often do you get chat with Ting Xu and other doctors?
Recently, it's very quite often for me.
How
Yes, because the analysis part, it's also need his
Yeah.
his,
once a week?
more than almost 1 day or,
Okay, because
or
that's
2
good.
days.
Yeah, it's very important to chat with doctors when we are dealing with medical project. Similarly, when we do biological project, we chat with Chief A and his supervisor very quickly. Or MIT collaborators on that. Yeah. So that's good. I feel like you are on the extremely exponential growth stage of your project. Don't miss this. Yeah.
No,
This is rare, to be honest. To be honest, this chance is yeah.
I'm little afraid that after my analysis, I find nothing. It's very
No, you have to do analysis
Right.
right away. I'm 100% sure this PCA results
Huh?
don't show you a very good RMSE or cross-entropy loss, right? But you have to evaluate the thing you biomarker you get in the way they are using for public health. Yeah, let's speed over to line. You hit 4 line.
Quick question. So
Yes.
Can you remind me how does they formulate the PCH?
Of
So that y-axis, how does they formulate it? They combine different parameters, variables.
Oh, you mean the definition of the PCH?
I mean, so for the y-axis, that's a scalar, right?
Yes,
So how does it get that specific value?
specific value. Oh, you which figure? You mean for example, figure D beginning.
Slide. Yeah, here. Next one, yeah.
This one?
Yeah.
Oh, yeah. This is PCH years.
Oh, you mean this?
Because you have principal components of 18 components, right? 18
Yes.
components. And you're saying this is.
I see. Oh, they have. You can see that they have the 18. The 18 components along with the CA. We use the Cox model to predict the each person risk of death. Yes, Cox. Yes, Cox model. It's a clinical traditional model.
Okay, I think
How
in a simple description of Cox model is like including whether someone die and how
Yes.
when he died. Time to events plus binary
yes.
death. Yeah.
Okay.
Yes.
So the input of the Cox model is the 18 total components.
Yeah, and there are CA.
And that is, and the output is the PCH.
Yes, I think after is the risk and he defines the risk. We call it PCH. Yes.
So that's a rule-based math. I mean, for the Cox model.
Cox model have parameters, so it's Cox model itself is printable.
I
But
see.
PCA of course is rule-based. And so I think the reason we can get a long tail is because of this linear model. Have not fit data well, so you can get the outlier. And you can get that those long tail. If you do an MLP directly from the feature space, the fit model for the video they are too good, then you won't have those long tail. Yeah. Interesting.
I'm curious about that. If we after doing some intervention, does the aging, the biological aging can be reversed? Reverse is the
Reverse. I think their results suggest you can slow down.
I mean, being younger, yes.
I mean, how do you do experiments?
I don't know, but
Oh, I
think
see your point. Oh, I see your point.
the biological age being
I
young.
think their
Biological.
experiment saying well, of course you cannot do this for same man, right? I cannot say Chilan, I give you diet. I give you burger. I give you salad. It's like a quantum. Okay, but you can do someone. The ideal case is Chilan's twin brother, but don't have it. So it's like someone have same BMI, age, and gender as Chilan, right? I think what in their result they show the one salad and do more exercise will be younger. Yeah.
I mean, for individual, if someone
What I said is what all you can do for individual if you don't have twin brother.
okay.
Yeah, because you cannot ask him to eat burger only
Oh,
and eat salad.
Yeah,
only.
that makes sense.
Yeah. So that's a difficult part of causality study in medicine because you cannot do this what if study.
But as I remember, I've heard and I've read something said after someone doing exercise or keep a good diet or habit, good habits, their biological age being younger,
Yeah, that's their solution. That's their observation as well.
being younger.
Yes.
I think he's saying that can you reverse your biological?
Yes, reverse,
Yes.
yeah.
Can you reverse your own? Oh, I see. Your point is not like a control study, right? Okay, if you do this, you can reverse your biological stage. At what point before you starting doing it or end up doing this? I'm curious about that.
Sorry.
Okay, if you start doing more exercise at the age of 20,
Yes.
you do it for 1 year, right? So do you want to answer the question whether your biological age will be younger than 21 or younger than 20? That's the question.
I mean, what I want to say is, maybe someone is, their physical age is, not like physical, their
Biological age.
no,
Yeah, chronological age. Yeah. Chronological
yeah,
age.
Say
the
it.
chronological,
Say it.
chronological age is 20, but their biological age is 40.
Yes.
Yeah.
And this kind of situation, when they doing some exercise or doing some diet, maybe their biological age will be reduced.
Yes.
Two.
Yes, the problem is that during the diet, the time is
Yeah.
still going.
Yes,
uh,
yes.
So it's hard. Yeah, the
Oh,
formulation is still on.
Yeah, you don't get like a 10 pounds off within a day, right?
Yes, yes.
You can see the results of this experiment. That is the red line is the group who was designed to test the effects of Caroline restriction. Yes, the red line. You can see that.
Yeah, you can see you are stopping your
Yes,
it's
in
stop
the-
agent.
On the stop age.
Yes,
Do it
and
now. Do it now.
the
That's
black
very,
line
very
is-
close to message, I think.
So if someone has a very old biological age, then his chronological age. So that means does this means he can never
I think this line suggests you can be a little bit younger, but
Mm.
overall you still get older.
Okay.
But if you do diet, if you are on diet and you do exercise, then your aging process become much slower.
Yes.
So once you will do for lunch today.
So there is this billionaire guy called Brian Johnson.
Yeah.
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 So stopping. Yeah, so he is taking some gold plasma therapy to reverse his biological age.
I think he's a good friend of our head of department on engineering side in Bo. I think this guy go to go to bed around 7:30 p.m. and from 7 p.m. he switch all the lights off. From 6 p.m. he put all the phone off and never look at the screen or moving picture anymore. And I wake up something like 4 or 5 a.m. I know exactly what time, then go to jog, swim kind of thing.
He never goes into the sun.
Really?
Yeah,
Really?
yeah. That's why his skin is so pale.
I'm not sure about that part.
Yeah, I
Yeah.
read that document again.
And you should talk to our head of department, Ting Xu, as well. He wake up at 4 a.m., starting sending me a message, and then he go to jog. He doesn't have breakfast. He go to jog around 5 a.m. Then he only have lunch and dinner, but it's like chicken without any sauce. Chicken vegetable without any sauce.
So how's his health situation now?
Okay, very can someone show a picture of Ting Xu?
Oh,
Ting Xu, yeah. As you are the department. I mean, you are not. Ting is not, but Hong Yu is the department. Yeah.
I think he's super healthy. He
Oh.
probably be one of the most healthy people
Ah.
I've ever met.
And I can show some YouTube videos of Hong. Okay, so
Yeah, you can send that to me.
we will know exactly how to healthy because Hong Yu is getting his personal data hourly measure of blood and so many biomarkers and so Hong Yu is going to make a machine learning model.
Yeah, I'm super looking forward to that project.
Yeah.
Interesting.
Yeah, so this is he's the head of biomedical engineering department in CDE, and in Singapore he's very famous for being fit. Yeah. Yeah. But I know in his office is the refrigerator, and there are the 2 bottles of wine inside of the so, apparently it's not only chicken and vegetables, also wine and other things.
Right.
Yeah, so anything else? Good, yeah, thank you so much for the presentation, very nice. And I can switch off this